Okay, let's jump in. We want you to take a moment and just think about your phone or your internet connection.
Maybe you're streaming something right now or you're on a digital call.
Exactly. All these things, these bits of everyday tech we totally take for granted, they really all trace back to, well, one person, one mind.
It's amazing, isn't it, how these really quite abstract mathematical concepts just became the foundation for everything digital.
Yeah. So today we're doing a deep dive into the life and, frankly, the incredible mind of Claude Shannon. People call him the father of information theory.
And he really did lay the groundwork for the entire information age. It's hard to overstate it.
And our mission here, using these fantastic sources detailing his life and his revolutionary contributions, is to sort of unpack the genius behind all the bits and bytes, that shape our world.
We'll explore how his ideas really transformed communication, computing, even AI.
And we'll get into some really fun anecdotes, too, about his personality, which is definitely quirky,
Yeah.
and some of his, let's say, unexpected inventions.
Oh, yeah, the inventions are great.
So let's start at the beginning. Claude Shannon, born April 30th, 1916, Gaylord, Michigan.
And right from the start, apparently he had this knack for mechanical things, electrical stuff.
Totally. Building model planes, a radio-controlled boat.
Oh.
Get this, he even built a telegraph system out of dark wire to his friend's house like half a mile away.
Just amazing kid stuff, but
Yeah.
foreshadowing, right? And his hero was Thomas Edison.
Who it turns out was actually a distant cousin. How about that?
Small world. So academically, he goes to the University of Michigan, graduates in 36.
With dual degrees, right?
Yeah.
Math and electrical engineering.
Yep. And then comes what many call the birth certificate of the digital revolution, his master's thesis at MIT in 1937.
Birth certificate of the digital revolution.
Yeah.
That's huge for a master's thesis. What was so groundbreaking about it? Was he already thinking beyond just circuits?
Well, yeah, in a way. See, electrical circuits back then, especially for things like telephone switching, were getting super complex.
Right. Hard to design, hard to fix.
Exactly. Kind of a mess to analyze systematically. Shannon's big insight in this thesis, titled A Symbolic Analysis of Relay and Switching Circuits, was realizing that Boolean algebra, the math of true-false, on-off, could be directly applied.
So using logic gates, basically.
He showed how you could use this algebra to analyze relay and switching circuits, simplify them, optimize them. It gave engineers a formal language, a mathematical tool to design digital circuits.
Ah, okay. So it provided the theory behind digital logic design.
Precisely. The foundation for all digital computers to come. That's why people call it possibly the most important and also the most famous master's thesis of the century. It wasn't just important, it was practical.
Gave us the blueprint, essentially. But he didn't stop there. His intellect was broader.
Oh, absolutely. He got his PhD in mathematics in 1940. His thesis was actually on population genetics.
Genetics?
Yeah.
That seems like a jump.
Yeah, it contained important results, apparently, but it mostly went unpublished. He kind of lost interest in the topic later. But around that time, he was also at the Institute for Advanced Study, rubbing elbows with giants like John von Neumann, Einstein, Kurt Gödel.
Wow. Imagine the conversations there, just soaking up that intellectual energy.
Right. So he's got this incredible foundation. He's met these amazing minds. Then the world heads towards war.
And what does he do? Where does that lead him?
Well, that practical side really kicked in. He joined Bell Labs in New Jersey in 41, stayed there for decades, until 72, actually.
Bell Labs, the legendary innovation hub.
Exactly. During the war, he worked on really critical stuff. Fire control systems for anti-aircraft guns, cryptography.
National defense work.
Yeah, and he invented something called signal flow graphs in 1942, which is a way to visualize and analyze complex systems like how signals move through circuits. Really useful tool.
Makes sense. Simplify the complex. And speaking of foundational figures, did he cross paths with Alan Turing?
He did. Turing visited Bell Labs in early 43. They met, talked. Turing showed Shannon his huge 1936 paper on the universal Turing machine.
The theoretical model of computation.
Yeah. And you can imagine that really resonated with Shannon's own thinking about computation and information, two giants kind of converging on these fundamental ideas.
And that cryptography work during the war, that led to another key paper.
It absolutely did. It started as a classified memo in 1945, a mathematical theory of cryptography.
Classified initially.
Yeah, because of the war context. It was declassified and published in 49 as Communication Theory of Secrecy Systems.
And what was the big takeaway there?
He mathematically proved that the one-time pad system in cryptography is truly unbreakable.
The gold standard.
Right. But crucially, he also showed that any unbreakable system must have the same properties. The key has to be totally random. It has to be, as long as the message itself, you can never reuse it, and obviously you have to keep it secret.
So he defined perfect secrecy mathematically.
Pretty much. It's seen as closing the book on classical crypto and really opening the door to modern cryptography, setting the theoretical limits.
Which leads us, I guess, to the absolute monster paper in the 1948 one, A Mathematical Theory of Communication.
The magnum opus, yeah. This is where he basically founded information theory as a field.
This feels like the moment. What were the core ideas?
Okay, so first, he formally introduces the bit, the binary digit, as the fundamental unit. We use that word constantly now. He's the reason.
0 or 1, the basic building block.
But the real genius was treating information itself as something measurable, like energy or mass. He came up with information entropy.
Entropy, like in physics, disorder.
Similar concept, but here it measures the uncertainty or the unpredictability, the surprise value in a message or a data source. The more random or surprising it is, the higher the entropy, the more information it actually contains.
Huh. Okay, so less predictable means more information content.
Exactly. Think about it. A message saying, "Erpele doesn't tell you much." A random string of letters has much more potential information.
Right, and he gave us a way to measure that. So, a universal ruler for data, regardless of meaning.
Precisely. And then there's channel capacity.
Which is
That's the maximum rate at which you can reliably transmit information over a specific communication channel, like a wire, or radio waves without errors, or at least with an arbitrarily low error rate.
the speed limit for data transmission.
The theoretical speed limit, yeah. Determined by things like bandwidth and noise on the channel. No matter how clever your modem or your Wi-Fi router is, it can't beat Shannon's channel capacity for that physical medium.
So he defined the fundamental currency of the digital age, the bit, and the ultimate speed limits for moving it around.
You got it. And that's why this paper is called things like A Blueprint for the Digital Era or the Magna Carta of the Information Age.
The impact is just. It's everywhere. Internet, phones, satellites, data compression.
MP3s, JPEGs, all rely on these ideas of measuring and reducing information redundancy.
Even understanding black holes. How does that connect?
Well, the concept of entropy in information has surprisingly deep connections in physics, including theoretical work on the information content of black holes. It's a testament to the fundamental nature of his ideas.
Wow, okay. Now, these ideas are pretty dense. Did anyone help make them more accessible?
Yeah, a guy named Warren Weaver wrote an introduction aimed at a broader audience when Shannon's paper was republished as a book, helped popularize it.
And Shannon himself applied it.
Oh, yeah. He wrote a fascinating paper, Prediction and Entropy of Printed English. He analyzed the statistical structure of English, showing how much redundancy there is.
Like how you almost always follows Q.
Exactly. He calculated the entropy of English and even showed that treating the space between words as a 27th letter actually lowers the uncertainty, makes prediction easier. Foundations for computational linguistics, really.
But even with all this, he was cautious about the hype.
Very much so.
Yeah.
He had this really strong scientific integrity. In 1956, he wrote an editorial called The Bandwagon.
Okay.
And he basically warned that information theory has perhaps ballooned to an importance beyond its actual accomplishments. He saw people applying it loosely everywhere and urged for rigor. Keep it scientific.
That's pretty grounded for someone who just invented a whole field.
Tells you something about him, doesn't it? He also, by the way, co-developed pulse code modulation, PCM.
PCM, what's that?
It's fundamental to digital audio, digital telephony. It's how you turn an analog signal, like voice, into a stream of digital bits. Absolutely essential for moving telecom from analog to digital.
It's just another casual invention changing the world.
Seems like it for him. But yeah, his genius wasn't just these huge theoretical papers or telecom standards. There was this whole other side, the playful, eclectic inventor.
Right, let's get into that. Because he was also a pioneer in artificial intelligence.
Definitely. He wrote a paper in 1950 programming a computer for playing chess.
Chess, okay.
It laid out fundamental ideas for how a computer could play chess, evaluating positions, exploring moves. It also estimated the complexity of chess, the Shannon number.
Oh yeah, that number. It was something like 10 to the power of 120.
That's the one. An absolutely mind-boggling number representing the possible game states or move sequences in chess, just showing the scale of the challenge.
Putting it in perspective. And then there was the mouse. Theseus.
Theseus the mouse.
Yeah.
Yes. Also in 1950, it was this little mechanical mouse, magnetic, running on a maze made of metal dividers.
And he could learn.
Yes, it used relays, essentially, to remember its path. It would explore the maze by trial and error, bumping into walls, until it found the cheese target. Then, on subsequent runs, it would remember the successful path and go straight there.
Wow. So it was literally the first electrical device to learn by trial and error.
That's what they say. A physical demonstration of learning algorithms. Huge inspiration for early AI researchers.
And he was involved in that famous Dartmouth workshop, too.
Right at the beginning, he co-organized the 1956 Dartmouth workshop. That's widely considered the founding event of the field of artificial intelligence. He brought together the key people thinking about machine intelligence.
So information theory, cryptography, AI foundations. But his day job was still professor at MIT later on and consultant.
Yeah, he became a visiting professor at MIT in 56, then joined the faculty from 57 to 78 while still consulting for Bell Labs.
Okay, now the really fun stuff. The hobbies, the inventions, the unicycle.
Unicycle.
Right.
Legend has it he would ride it down the halls of Bell Labs.
Well, juggling.
Sometimes, apparently augmenting the hazard by juggling. He loved unicycles. He didn't just ride them, he tinkered with them.
Like the motorized pogo stick?
Yeah, he built that too.
Yeah.
Said it would replace the unicycle that his colleagues were so nervous about.
I bet. What else?
He made a two-seater unicycle and one with the hub off-center so the rider bobbed up and down like a duck. Just playful engineering.
That's brilliant. And it went beyond unicycle.
Oh, way beyond.
Yeah.
He built juggling machines, actual robots that could juggle, a machine that could solve a Rubik's Cube, which is non-trivial.
Seriously. A Rubik's Cube solver back then.
Yeah. And then there's the more eccentric stuff. Flame-throwing trumpets.
Wait, what? Flame-throwing trumpets?
Apparently so. Rocket-powered frisbees. And those shoes. Plastic foam shoes designed so he could appear to walk on water across his lake.
You can just picture him doing that, can't you? He also made educational toys.
Yeah.
Right?
Yeah, the Minivac 601. It was like a digital computer trainer kit for business people using simple relays and switches to teach basic logic, making it accessible.
And the wearable computer for roulette.
Ah, yes, him and Edward Thorpe. They built a small, concealable analog computer, timed the ball and wheel, tried to predict where the ball would land. Apparently it worked, though they had technical glitches.
First wearable computer used to beat the house. Classic Shannon.
And speaking of beating the odds, his investment record was apparently phenomenal.
Right, the Shannon's Demon strategy. What exactly was that? It sounds mythical.
It's based on a theoretical idea. Imagine you have an investment that fluctuates randomly and cash. The demon strategy involves constantly rebalancing between the two, selling some of the asset when it goes up, buying more when it goes down, capturing gains from the volatility itself.
So exploiting the fluctuations.
Exactly. And reports say his application of this, or something similar, outperformed almost all mutual funds, even Warren Buffett for a stretch, applying mathematical insight to finance.
Just another field he mastered on the side. Incredible. So how is all this recognized? Did he get the accolades he deserved?
Oh, yeah, plenty of honors. The Alfred Nobel Prize early on, the National Medal of Science in '66, the Kyoto Prize in '85, Marconi Lifetime Achievement Award in 2000, right near the end.
And statues.
6 of them, I read. At Bell Labs, they even named the Shannon Labs after him, MIT, Michigan, Gaylord, recognizing his impact.
Which is just immense. Some say his work is as fundamental to our tech world as Einstein's is to physics.
That's a comparison you hear a lot, single-handedly creating information theory, laying the digital foundations. Comparisons to Newton, Darwin, too. It's that level of paradigm shift.
His fingerprints are just everywhere. Every device, every screen, every digital message.
Totally. Often invisible, but completely essential infrastructure for modern life.
Sadly, he struggled with Alzheimer's later in life, didn't he? He passed away in 2001.
Yes, a quiet end for such a profoundly influential figure.
So wrapping this up, what does it all mean for you listening? Well, Claude Shannon's deep thinking about information, how it works, how you measure it, how you move it, it has shaped basically every single interaction you have with technology.
Yeah, from that tiny bit he defined up to the massive global communication networks we rely on, his theories are the invisible scaffolding. They just work behind the scenes.
And it makes you wonder, doesn't it? If the guy who gave us the mathematical bedrock of the information age also invented rocket-powered frisbees and walked on water.
What else is out there? What other huge breakthroughs might be waiting, maybe hiding in plain sight?
Exactly. Maybe discovered by someone willing to be brilliant, a bit eccentric, and look beyond the obvious, just like Shannon did. What are we missing? What could redefine our future?